Hey guys, Miss Peterson here, and welcome to lecture 14-2 about mechanical waves and sound. I'm going to call this my guitar lecture. In this lecture, we're going to be talking about both mechanical waves on a string and how they behave, getting into standing waves and harmonics. But then we're also going to be talking about sound and what sound is and how that works. So let's go ahead and get started. Now, have you guys ever seen these videos of the strings from inside a guitar? And you see those waves and how they're made. What do you know about that? How does it work? How do we tune a guitar to produce the exact frequencies that sound like music to our ears? And why does just a little pluck of the string cause it to be able to reach our ears? Let's get into it. Let's start with the actual waves on that string. Now, when we're talking about waves on a string, they are obviously mechanical waves. That is the actual particles of the string that's moving, formed by a point or an oscillation at any point on it, okay? You pluck the guitar, the energy from that vibration moves outward and vibrates the rest of the string, okay? Remember, it's not that the string... that like the actual matter of the string is moving. The matter of the string moves perpendicularly as the wave moves through it. Okay. Now for strings, because we use them so often, we actually have a set equation for those. Now, the equation that we use for waves on a string is that the velocity of the wave on a string is equal to the square root of the force of tension divided by m over L, okay? So we have the speed of the wave, okay? We have Ft, which is the tension in the string, and that makes sense, okay? I have a rubber band here. If you flick the rubber band, okay, and then change the actual tension in the string, you can feel how that wave acts differently, okay, due to that difference in tension. Higher tension tends to make it go a little bit faster, where m is going to be the mass of the string, and L is going to be the length of the string, okay? Sometimes they'll give these to you together as the mass per unit length. Okay, very similar. You can think of it as like the density of the string. It's just in terms of the length of the string rather in terms of the volume of it. Okay, so it is a square root relationship, but the tension, obviously, if you increase the tension, you're going to be going faster. And then the mass per unit length is on the bottom of that equation. So if you have a bigger mass per unit length, you got more particles you got to move around, okay? That's going to make it slower. Okay? Okay, cool? Okay, cool. So we got this wave. It's moving on a string, and eventually it's going to hit something, whether that's the top of the guitar or whether it's the ocean wave hitting the sandy beach. And one of the things we need to know is how that wave is going to behave when it hits that. So we're going to go ahead and look at a simulation. So this is the PhET simulation for waves on a string. Okay, I have it on, we'll start it on pulse. Okay, and right now I have no end. We're going to go ahead and give it a fixed end. So if I send a pulse, we'll change it into normal mode down that. One more time, zoop. We see that that pulse gets reflected and inverted as it goes back. So go ahead and draw that in right here. Okay, gets reflected and inverted. Draw it in. Now for the loose end, okay, let's go ahead and change it to a loose end, and let's see how that one behaves. So we got the and it goes on back, zoop, and back. Now, it's going with a lower amplitude because the simulation is a little bit realistic. We have some dampening on. If we turned it to no dampening, we wouldn't see that change in the amplitude of that wave. But here you're seeing the reflection on the loose end without the inversion and the reflection on the fixed end with the inversion. So go ahead and draw both of those on your sheet. Okay. Now, sometimes the wave is still going to be like transmitted. It's not going to be a pole there. Maybe it's something more, a thicker string, something like that. So let's go ahead and look at this simulation. So this is a simulation from physicalclassroom.com where we have different relative densities. And we're going to start with a transmitted wave going from a low dense medium into a more dense medium. So again, this one, I have it on the least density for a medium one. And then this one, represented by those fatter points, have the higher density. So when we run that simulation, we see that some of the wave is reflected with that inversion, similar to the fixed end. And some of it gets transmitted into that boundary with a smaller amplitude. So go ahead and watch it one more time. Reflected, inverted, and then transmitted with a smaller amplitude. Okay, so go ahead and get that one drawn. And let's go to the last one when we're going from a relatively dense medium to a least dense medium. Well, let's see if you can make a prediction. What do you predict is going to happen here? Okay, let's go for it. So we see that wave approaching. And similar to the loose end, we're getting that reflection without the inversion. And we're still getting that transmission with that smaller amplitude. Go ahead and watch it one more time. Okay. We get a wave being transmitted with a smaller amplitude and a wave being reflected, but without that inversion. Okay. Now, Physics Classroom also has a concept checker, which is a little game you can play to test your knowledge of this. So yeah, I recommend play with it, test it, get this to sink into your brain. Those boundary behaviors. Okay, cool. Okay, cool. Let's go ahead and talk about harmonics, because how do those waves actually form? You might have noticed at some points in that song, the wave looked like it was standing still. And that's because if you have a string with a fixed end and it travels along that, well, it could be inverted and go back and interfere with itself. We'll talk about interference a lot more in the next lecture, but the basic of it is if we have two crests, okay, two tops meeting, then we're going to get constructive interference. The amplitude is going to be a lot higher. Where in destructive interference, okay, you get a nothing, okay? You get like no amplitude. The wave goes away for a brief second, okay? So if that's happening along the length of a string, what can happen is something called a standing wave, okay? Now, this can happen when the wavelength is an exact fraction, either 1 or 0.5 that length of the string. Okay. Now, the fundamental is the first harmonic, and this is the one that instruments primarily play. If you don't know which wave it's happening on the string, it's going to be that first harmonic. Now, you can see here, this is only 1/2 of that wavelength. So for the first harmonic, okay, that first harmonic F, the length of the string, which we typically call L, is equal to 1/2 of the wavelength, okay? Now, for n equals 2, that's when the length of the string equals the wavelength of the wave. At n equals 3, the length of the string will be equal to 1.5 times that wavelength, etc., etc. So you can see how those standing waves are created to appear stationary. And let's go ahead and look at that in the simulation as well real quick. Okay, back to the waves on a string. I'm going to go ahead and give it a fixed end so that we get that inversion. And I'll go ahead and reset it here. Now I'm going to change it to oscillate. Okay, we're going to turn down the dampening so we're not seeing much of that. And automatically you can kind of see it start to happen, but then it gets a little funky. So my goal is for this wave to look like it is standing still. So I'm going to try lowering that frequency a bit. In playing around with the simulation earlier, I was able to find it around 1.25 hertz. Okay, there we go. We're just about at that third harmonic. We can see one full wave and that last one. And obviously, see this amplitude is ginormous compared to the little vibration of this. And that's because of that constructive interference. This, if it was a sound wave, would be loud, okay? So we can see how that can kind of happen. Let's see if I can turn the frequency up and find another harmonic of this one. Oh, might be a little hard when it's been going for a while. But let's see if we can get something else looking like a harmonic here. See that wave moving? It's not staying in one spot. So we're not quite on that harmonic yet. We'll turn the dampening down so it's a little bit more. Okay, closer. Okay, let's put it in slow-mo. I don't know. I think I see that wave moving just a little bit, but it's pretty close to that full harmonic, okay? Again, that standing wave is when that wave just seems to stay in place. It doesn't look like it's traveling at all. This one's traveling a little bit, but we are definitely getting closer there. Let's see, can I find it? There we go. If this was it, would be the 1, 2, 3. We got 3.5 waves there. So it would be the 1, 2.5 waves is the 5th harmonic. So 3.5 waves would be the 7th harmonic. Okay. But again, this fundamental frequency where the length of the string is 1/2 the wavelength will be really important in a lot of applications involving instruments. Okay. So let's go ahead and apply this to a piano tuner. Okay. How piano tuners actually work is they have a tuning fork and they can match the sounds and those frequencies and adjust either the little tines that you tune on a guitar or actual cranks and stuff in a piano. You change that density and that tension in the string to produce the sound you want. So he's adjusting that tension to produce the note middle C, which has a frequency of 261.63 hertz. The string has a length of 1.5 meters and a mass per unit length, okay, that's where they're giving us it together, of 0.01 kilograms per meter. And we want to know the correct force of tension in the string to produce that frequency, okay? Well, what are we going to need? Well, we know the equation. We got that one right up here. We have the velocity of the string and that square root. So we're going to need the velocity of that string, the velocity of the wave in the string. And the way that it's given to you is in the length of the string. To produce that loudest sound, we are going to want to do the first harmonic. Okay. That's going to be the primary note, the primary frequency that string will play. So then we know that the wavelength of it is equal to 2 times the length. Because again, the length of the string is half the wavelength. So then if you want to know the wavelength of it, it's going to be double the length of the string. Okay. So we can go ahead and find that wavelength. That wavelength will be 2 times 1.5. So we want to produce a wave with a wavelength of 3.0 meters. Okay. And again, we are looking for that force of tension. Okay, so we have our equation. Our equation is that the velocity on a string equals the square root of the force of tension divided by m over L. And then we also know that the speed of any wave, whether it's a wave on a string or a light wave or a sound wave, is equal to wavelength times its frequency. So we can use both of those equations together to solve for our force of tension. And let's go ahead and put these together so we can do a little bit of derivation practice. Okay, so we have that the wavelength times the frequency equals the square root of the force of tension divided by the mass per unit length. To undo the square root, we're going to take the squares of both sides. So we have the wavelength times the frequency squared equals the force of tension divided by that mass per unit length. Okay, so the force of tension will equal the wavelength times the frequency squared times the mass per unit length. Okay, so we have our wavelength, we have our frequency, and we have our mass per unit length. So then it's just plugging those all into your calculator. So we get the wavelength, which is 3 meters, times the frequency, 261.63 hertz. We're going to take that number and square it, and then times it by the mass per unit length, so by 0.01. And we get 6,160 newtons. Okay, so a pretty tense string. Okay, cool. Okay, cool. By the way, how can you hear me? What is sound? So this is a virtual oscilloscope. What you guys are seeing is a graph of the sound wave that I am producing, with my vocal cords. You see me talking and we can see that sound wave. Now, obviously, this isn't going to be a pretty sound wave. There's a lot of different tones, a lot of different pitches, a lot of different frequencies going on that we use to shape our words. Now, I'm not a singer, but let's see if I can get something similar to what music looks like on an oscilloscope. Okay, let's hum. Ooh. Okay, let's try one more. Oh. Better at the lower ones. But you guys can see when I'm humming that low kind of monotone one note, you're seeing a more organized wave pattern. Now, instruments are characterized by the wave patterns that they produce. And our notes that we know, whether it's a C or an A or a D sharp, is determined by that frequency. And it's all just based on this sound wave that's created by whatever's vibrating. Now, my vocal cords can create the sound, but any vibration can create a sound, whether you're drumming on something, okay, whether you're snapping your fingers and vibrating that air, anything can create a sound. And again, it is a longitudinal wave, so it's composed by areas of high density. So compression means high density air or higher density air. And rarefaction, which is going to be the lower density air. Now, sometimes you will see this represented like a transverse wave. And just think of this y-axis as the pressure, okay, or the density, whichever you like to think of it. High pressure, closer together air molecules, high density, higher, closer air molecules. So that's what's going on with all the sounds that you hear in the air. Now, if I want to talk louder, okay, if I want to talk louder, you can see that that's a high amplitude. Where if I whisper and I talk really, really slowly and quietly, that's going to be a low amplitude wave. Okay. Volume is going to be related to the amplitude of the wave. Wavelength, just like in Any other wave, it's that distance between two similar points on the wave, either two successive compressions or rarefactions. And most of the time, we will be talking about sound in air, where it has a speed of 343 meters per second. Okay. Now, we talked a little bit about that tuning the piano, okay, and how we can adjust the strings to do that. Now, how we actually figure out how to do that actually has to do with beats, okay? Now, I'm not talking about the beat that a musician might lay down under their track. I kind of am. But this is a beat that's created by two slightly different frequencies. Basically, if you have two different sound waves, okay, there's going to be spots on the sound wave where the crests line up, okay, where the crests line up. And you're going to get constructive interference, okay, like there and there. But then there's also going to be places, I'll go ahead and go blue for these ones, where a crest meets a trough, and you're going to get destructive interference, a low intensity wave, okay? Now, this has to do with how out of phase, how different those wavelengths are. So the actual equation for it is on your equation sheet. It's that the beat frequency equals the absolute value of the frequency of one divided or minus the frequency of the other, okay? It's an absolute value because you can't really tell which one's the one moving faster versus slower, which one is 1 and which is a 2. But it's the difference between them that create those, okay? You can see it kind of represented graphically here. And hopefully you can imagine how we can use those equations and those functions that we could write for our waves and for our sound waves in order to engineer the sound to be exactly how we want to. Okay. But here you can see, again, those places where it's completely out of phase, where you have a crest on one wave meeting a trough on another wave, and then places where it's completely in phase. Okay. Use yellow for that one, where you're getting a crest on one meeting the crest on the other and getting that higher amplitude wave where the amplitudes will add, okay? And the waves in general will add. You can also kind of picture this. That's how the actual tuning fork itself works. Obviously, one little small vibration has trouble producing a lot of sound, but when you have those two prongs of the tuning fork, you're going to get areas of that high intense sound and areas of the low intensity sound. So different people in the room will hear it at different times, but it's just because of when those sound waves are hitting you. Okay? That makes sense? Okay, cool. So you're tuning a car by comparing the sound of the string to that of a standard tuning fork for your desired frequency. You notice a beat frequency of 5 hertz, okay? So we know that the beat frequency is 5 hertz, okay? As you tighten the string, so if you're tightening the string, that means the force of tension is increasing. Then we get the F beat rises to 8 hertz. So we're getting more of a difference between the strings. Now, if we were listening, we were hearing that, should we tighten the string? Should we loosen the string? Or can we not tell? Well, let's go ahead and look at this a little bit closer. Okay. We know that the velocity of that wave on a string is proportional to the force of tension divided by m over L. So if the force of tension is going up, we know that the velocity of the string is also going up. Okay. Now, velocity equals a wavelength times frequency. So if that velocity is going up, we know that frequency is going up as well. Okay. So the frequency, the speed, the frequency of the wave must have increased when we tighten the string. Okay. Now, if increasing that frequency made the problem worse, okay, it made it so it was more difference. Okay. So when that frequency increased, there was more difference between the frequencies, more of that frequency. They got farther away from each other. So to get them closer to each other, then we should loosen it. Which kind of makes sense, obviously. We need to go the other direction. But again, the reason for that is because if we loosen it, that is going to then decrease that frequency and bring our two closer together. Okay, so if F1 is our F beat minus 5, and then here we have F1 is going to be F beat, or 8 minus F2. Trying to make it, I'm making it harder than it needs to be. You guys got it, okay? You tightened it. It made the problem worse, so we need to loosen it and make the problem go the other way, because tightening that increases that frequency. We want the frequency to be lower so we get less of a beat. Those frequencies are closer together. Okay, cool? Okay, cool. One last thing to talk about with regards to sound, which is the Doppler effect. Highly recommend you watch Dr. Sheldon Cooper from The Big Bang Theory explain the Doppler effect. I'll link that video here. But the Doppler effect is that when the source of a sound is moving, like say an ambulance or a fire truck, okay, the frequency seems to change from your perspective, which you might know intuitively. If you were standing on the street and heard sirens, would you be able to tell whether the sirens were approaching you or going away from you? Most likely. We do this when we're driving all the time, so we know whether to pull over or not. And that's because of the Doppler effect, okay? When that sound wave is being emitted from that speaker, if you are in front of the source of the sound, the waves get squished together and you get a higher frequency. Where if you are behind the source of a sound, those waves are getting more spread out. So you're getting a lower frequency. Okay. And again, it is the speed of sound is constant. So this will also affect the wavelength. If we have a higher frequency, we're going to have a shorter wavelength. And with the lower frequency, we're going to have a longer wavelength. Now, the AP Physics 2 curriculum does not require you to do the math of this, but I will go ahead and show it to you just so you guys know where it comes from. So the frequency of the observer here will equal the frequency of the source multiplied by the ratio of how much it changed. So we know if it is approaching you, then the velocity of the source, okay, is going to remove some of that velocity from the sound wave, or if it's moving away from you, okay? So if you are observing it, you can add that to the speed of sound if you were like chasing this sound, where the velocity of the source is moving away from you. So minus the velocity of your source to get the difference in how those velocities would be perceived. Okay. So yeah, the frequency that you observed will equal the frequency of the source times that ratio of the differences in the speeds. Now, you might also hear this be used in astronomy. This is called redshift and blue shift, and it's due to the light from the galaxies. So we study the spectrum of light from galaxies. And if a galaxy is moving toward us, then we say it is blue shifted. Where if a galaxy is moving away from us, we say that its spectrum is red shifted. We'll see all of its light characteristics, light waves, get longer. And we know that it's moving away. That's how we have evidence that the galaxy and the universe is expanding. Okay, so that's it for guitars, sound waves, and the strings that create them. Okay, cool. Okay, cool.